Welcome back to our study of using your calculator and derivative tests in order to sketch some more sophisticated, more complicated functions. Again, this is kind of the best scenario of an engineer, a good example of engineering where engineer using his knowledge of physics and math along with technology in order to get a picture of a problem that he's interested in. So at the top here, what should we start? Let's start with blue here. You see the problem here. We've got this function, and it's what we call a rational function, meaning the numerator is a fourth order polynomial, and the denominator is a polynomial too, in this case a second order. Now I started off just cranking out a derivative, okay? So here's a derivative. See that? Now, if I didn't have a calculator, I might say, well, I got to set this equal to 0. How would I set that equal to 0? Well, I set the numerator equal to 0. And it could be done. You see here we're going to have, what, a fifth order polynomial. Ouch. So you could graph that on your calculator. It gets nasty. It gets nasty in a hurry. So in that case, you might say use your calculator and your brain. Okay. So a little helpful thing we're going to use, first thing we're going to say, let's use some asymptotic analysis too. What do I mean by that? Well, what about a horizontal asymptote? Horizontal as and I'll say totes as in plural because in this case I just want to say what's the limit as x goes to infinity of f of x. And you'll see that's an x to the fourth plus ... over x squared. And in our study of this, you know that since this is fourth order, this is second order, this goes to the infinity, it's dominated by the higher order terms. So as x goes to infinity, it approaches infinity as x squared. Okay? It approaches as x squared. So as x goes to infinity up here, let's just say, well, we know as x gets larger out here, right, this thing's going up positive. Now what about as x goes to negative infinity? Well, because it's x squared and not x plus ... it also goes to infinity as x squared. So out here, bam. So I know what happens out as x goes to positive infinity and a negative infinity. They're both going up to infinity. They're both curves are shooting up to the ceiling. Okay, well, let's now use our calculator and see what kind of pictures we can get on our calculator. All right, and you'll see that right here. Look at this picture. If I just put my curve in, now notice here's your screen, your TI screen. Notice this small equal sign means it's plotting. The longer equal sign means it's not plotting. So you could leave this in. You could leave the first derivative and the second derivative, right? This is f prime of x. This is f double prime. You could leave those on your computer and just turn them on and off. Notice this curve here is pretty hard to see anything. Pretty hard to see. So let's plot a derivative and see what happens. And here we go. Okay, so now notice I turned on the first derivative. So here I turned off the original curve. The curve gets too messy sometimes. You could also make these things, as I told you, you can make this a heavier line. But what I'm looking at here is f prime of x with some asymptotes. Okay, well, looking at the first derivative, you got to be able to tell me something about the curve. What about here? This, I got, let's see, that's a min, right? It goes from negative to positive. That's a min. That's a min. The derivative goes from negative to positive. That's a min. Derivative goes to negative and positive. These are mins. Okay, let's try to change up here. We'll go red for maxes, huh? This, look at the derivative goes from positive to negative. That must be a max. And that must be a max. Okay, you see anything else? By looking at the first derivative, we can also tell where the inflection points are, right? We've talked about that. The inflection points, you'll see it's where the first derivative goes from decreasing to increasing. There's an inflection point. And here's an inflection point. Okay, so in green. All right, well, do we have enough to get a sketch? Do we have enough to get a sketch? Oh, I think, you know what, I'm going back to the other one. Let's leave this thing. Oops. I didn't put in my vertical asymptotes, did I? Forgot about those. Sorry about that. I did my horizontal asymptotes. What about vertical asymptotes? Here you'll see in the denominator I've got some zeros at -3 and 2. So I've got to put in x equal -3. -3, this is, and x equal to 2. So you got to keep those vertical asymptotes are going to be there. They're also going to be there in the derivative. Okay, back to my derivative now. Back to a sketch. Okay, let's try to sketch in the curve now, knowing over here, I started off by, let me get my blue pen. I put in my asymptotes here. That's my horizontal asymptote. Here's my vertical asymptotes. And now I'm looking at the derivative. I start over here at the negative side. Well, what happens? This thing's negative, right? It's negative till it hits a min. So it comes down. It's going to come down till it hits a min, and then it gets positive again. And you know what happens at an asymptote? It starts going off to infinity. Okay, so there's my first min. That's the min. That's the one min over here. Now look what happens on this side. I go here and it's positive. Okay, so the derivative is positive, so it means it must start here, and it's going to hit a max. So it's going to be positive, positive. It's going to hit a max. Okay, that's my max here. This is that max. It's going to hit a max, and it's going to hit an inflection point. It's going to hit a min over here. It looks like 0. Again, I haven't filled in anything. I'm just looking at the sketch here. That's going to hit a min about at 0. About at 0 here. And let me... Okay, we are using the derivative to sketch out our function over here. Pens, we're going in blue. This is f of x is in blue. And we just went through our max. Our max would have occurred right here. And we're going to go through inflection point. A min looks like it's happening at 0. I haven't really checked this, but looks like we're going to go up, and we're going to have a min here. About at min at 0, that's the other blue spot. We go through an inflection point and get to a max here. We get to a max in red. Okay, I'm looking over here, and then that goes negative. So what happens at the asymptote? It has to go through like this. Okay. Has to go through that. This is, let's do this in red. We'll color code it here. Okay, so we got our mins here at 0, and we got a min here, and we got another min over here, don't we? And I'll just put it in like here. I haven't drawn that so far. And then we'll go back here and go to a pen red. Where's our maxes? Well, our maxes are here and here. Okay, now let me finish drawing the curve a bit, and we'll put in our inflection points. So you see here, look what happens at the derivative right here is negative, right? So right after the asymptote, maybe I should draw in the asymptotes over here too. These are the asymptotes right in here, okay? You used to get, okay, those are the asymptotes. And now back to blue. You'll see it's negative here, so this thing is actually coming down like this, goes through a min, and then goes up. Okay? And that's basically my function. Now, do I know these points? All these curves, this curve could shift up or down, right? All these curves could shift up or down. I don't know the absolute value. what the y values are. I'm just getting the look of them. Let's see if the inflection points make sense. I got an inflection point between the max and the min, so I got one right there, and that makes sense. It goes from concave down to concave up, and then I should have another one between here and here. See, this goes from concave up to concave down. That makes sense. Okay, so what did I do? This picture of the derivative and my knowledge of looking at the first derivative, I was able to get a sketch of the function. Let's see what else I have on this thing. Okay, so and there is kind of what I came up with, right? That's kind of what I came up with. And let's see if all right, new problem. Okay, so we will see you soon. Bye-bye. Okay, here's a skill that you need to be very good at. And the skill here is looking, what I've drawn here is I'm looking at the first derivative, okay? I'm looking at the first derivative, and from looking at the first derivative, I want to find the max, mins, the inflection points on the original function f of x. That's the skill that you had to know in order to do the last problem. So let's just review that again. Now notice here, I've just got these are x points, A, B, C, D, and I've got E, F, G, H. If I look for mins occur when the first derivative goes from negative to positive, okay? So here, we'll work this a little bit. This goes negative to positive. So that's a min. A is a min. No, that's not, okay, C, negative to positive. C is a min. How about D? Oh, well, D does not change signs. It goes from positive to 0 to positive. So that's not the case, and this is, okay, so my mins are A and B. How about maximums? Maximum occurs when the first derivative goes from being positive to being negative. Well, here, how about this point right here? Positive to negative, sure, that's a max, B. How about D again? Nope, D is not. D goes from positive to 0, so that's not inflection point, not a max. So it looks to me like I've only got one max on this, unless you want to call this, but I didn't label it. So I guess we could call that I, and then I could put I up here. Okay, what about inflection points? Well, what's an inflection point determined by? It's the second derivative, right? The second derivative is just the slope of this first derivative that you're looking at. So you see right here, the slope of this is positive, right? So if I was going to draw, let's do this in blue. The slope of this is positive, so this should be, it's concave up. So when I draw an arrow going up, I mean concave up. Then it crosses through E, and then what happens? It goes concave down. So guess what? At this max point here, that's an inflection point. I'm going to have a lot of those. So E is going to be an inflection point. Same thing as you see, the concavity here is still down, but here, all of a sudden the slope of the first derivative, which is the second derivative, goes positive. So this arrow goes up, meaning from F to G, it's concave up. What does that make F? Makes it an inflection point. Okay, we're looking for more inflection points. You see from F to G, the slope of the first derivative is positive. So that means the second derivative is positive, and that means that it's concave up. Here, you'll see it goes from concave up at G to concave down. So guess what? G is an inflection point. Now I go down through D. D, this is still concave down. But right through D, the slope of the first derivative goes from negative to positive. So the second derivative goes from negative to positive, and D is an inflection point. Notice that D was not a min or a max. It's not a min or a max because the first derivative does not cross through 0. Okay, now we got point H. Now this is little H, again, goes from concave up to concave down on the first derivative. Okay, so H is an inflection point. Now, some people might say that, yeah, you're right. The second derivative at H does not exist. If you said that, you would be correct, because it's a spiky, like an absolute value type of point there where you cut your finger right on that cusp. The second derivative doesn't exist, but the inflection point is on the original function itself, and that point does exist. So H is an inflection point. So there you go. Your inflection points are E, F, G, D, and H. And you can see where your mins are. Your mins are at A and C, and you got a max. Your maxes are at B and I, if that crosses through. Okay, we'll see you soon. Sorry for going too long.